Okay, so now that we've talked about conservation of momentum, you've seen one example, let's look at a whole bunch more examples just to practice this. And let's go through the steps each time for how to know or how to solve a conservation of momentum problem. Number one, a 4 kilogram stationary cart on the track being hit by a, is on the track, is being hit by a 2 kilogram cart moving to the right at 3 meters per second. The carts collide elastically with the stationary cart moving off with a velocity of 2 meters per second to the right after the collision. What is the velocity of the cart that was initially moving? Okay, so we have sometimes all the numbers get a little confusing. So let's talk about what we're going to label these. I usually like to make whatever was moving initially in these types of problems. Let's make that cart number 1. So let's label this M1. So therefore, this 4 kilogram stationary cart, that's going to be M2. And it's stationary, so V2I is 0 meters per second. This, therefore, must be V1I. The carts collide elastically. The stationary cart moves off with a velocity of 2 meters per second to the right after the collision. So this is V2F. We are looking for V1F, the velocity of the cart that was moving in the beginning. Our first step is to verify that momentum has been conserved, that there's no net external force acting on our carts. They're on a level track. There is no talking about friction. There's no one pushing these carts. There's no springs or strings or anything else acting on them to cause a net force in the direction that they're moving in. So we can fairly safely assume that PI equals PF. There are 2 carts in the beginning and 2 carts at the end, so I'm going to expand this temporarily to P1I plus P2I equals P1F plus P2F. And since I'm not told the momentum of anything off the bat, I'm going to expand this further in terms of masses and velocities. So that's M1V1I plus M2V2I equals M1V1F plus M2V2F. And if this seems like a lot of writing, you're going to get used to it very quickly, okay? It's pretty straightforward. M2 was not moving initially, so I'm going to cross that off, and that's now going to be 0. M1, the cart that was moving initially, has a mass of 2 kilograms. And, oh, we need to set a positive direction. M1 was initially moving to the right, so let's do that. Let's say that right is positive. Okay, so that was moving at a speed of, what do we say, 3 meters per second to the right. We're looking for M1's velocity after the collision. And we know that M2, the stationary cart, which is a mass of 4 kilograms, ends up moving with a velocity of 2 meters per second, also to the right, after the collision. So, 2 times 3 is 6, equals 2 V1F plus 8. I subtract the 8 to the other side. 6 minus 8 is negative 2. Negative 2 divided by 2 means that negative 1 meters per second is the final speed of the first cart. And just in parentheses, the negative means that it must be to the left. Okay? Basic conservation of momentum. Let's look at the second one. A hockey player skates north. A 70 kilogram hockey player skates north with a speed of 7 meters per second. Another hockey player of unknown mass skates south to hit him with a speed of 9 meters per second. The players collide elastically. After the collision, the 70 kilogram player has a velocity of 9.5 meters per second south, and the player with the unknown mass has a velocity of 5.5 meters per second north. What is the mass of the unknown player? Same sort of situation. We have, I'm assuming that this is flat ice. There's no friction to speak of. There's no other force. There's no hint of any forces that could make this a case where momentum isn't conserved and there is a net force. So we're going to go again with PI equals PF. I know that I have 2 separate players before and after the collision because they collide elastically. So that's P1I plus P2I equals P1F plus P2F. And I'm not told anything about their momenta. So once again, we're going to expand out to the masses and the velocities. This time I don't think either of them was stationary to begin with, so we don't have anything that can cancel out. And we're looking for the mass this time, which is a little different from before, but everything should still work out just fine. Mass of the first player, let's make that the guy that we know the mass of. So M1, let's say, is 70 kilograms. Oh, we need to specify a positive direction. He's skating north. There's no real reason to make either north or south positive, but you got to pick one. Let's make north positive. So the 70 kilogram skier is initially skating north at 7 meters per second. Another hockey player of unknown mass, so I'm just going to leave M2 as is, skates south to hit him with a speed of 9 meters per second. Since he's moving south, it's going to be negative 9 meters per second. After the collision, the 70 kilogram player has a velocity of 9.5 meters per second south. Remember, he was skating north initially. Now he's skating south, so he's rebounding off that collision. Since it's south, we're going to put a negative sign there. And the player with an unknown mass, so that's M2, has a velocity of 5.5 meters per second north. So we want to find out what M2 is. Well, this might look a little confusing because you have M2 in two places, but that's no different than you've had in tons of math problems in your math career. Let's get everything else done first, though. 70 times 7 is 490, minus 9 times 2m, or M2, excuse me, equals 70 times negative 9.5 is negative 665. M2 times 5.5, well, okay, plus 5.5 M2. What your math teacher would now tell you to do is collect like terms. Anything with an M2, get it on one side. Anything that doesn't have an M2, get it on the other side. Easiest way to do that is add 9m to both sides and add 665 to both sides. You can do those steps right at the same time. 490 plus 665 is 1155. 5.5 plus 9 is 14.5 M2. And we divide by 14.5 to figure out what M2 is. Turns out that M2 is 79.66 kilograms. Okay, so we just found the mass of the other hockey player using conservation of momentum. Now, could you have done that using forces and kinematics? Yes, you could have. Would have been very difficult to do so. Okay, this actually, even though it doesn't look like it, saves you some work. Otherwise, you would have had to have found a bunch of accelerations, and I don't even think you have enough information. It would have been very difficult. Let's do two more examples. I think this first example that we're going to have is an example of what we would call in physics an explosion. Oh, nope, not yet. Okay, no, we're going to have an inelastic collision question. A 0.005 kilogram bullet is fired with a velocity of 400 meters per second. It strikes and embeds itself into a 3 kilogram wooden block that is initially hanging at rest. What is the speed of the wooden block with the bullet inside just after the collision occurs? Again, in this case, there's no friction, there's no external net forces. You might say, well, but the bullet's got to exert a force on the block. If we're doing conservation of momentum, then the bullet and the block are our system, okay? That's our system that we're looking at. Any force that the bullet puts on the block is internal to our system. So there is no net force. I'm therefore able to start here. Pi equals Pf. Initially, there's two separate objects, bullet and block. So I'm going to do P1i plus P2i. But at the end, there's only one object. The bullet and the block are together. They're embedded. If the bullet moves, the block moves along with it. Okay, so we treat that as one object. So I'm just going to keep this as PF. M1 V1I plus M2 V2I equals, since the bullet and block are combined, we combine their masses, M1 plus M2 V. And we are looking for the speed of the bullet and block just after the collision. So we're solving for V here. We do need to come up with a positive direction. So let's just say we don't have north, south, east, west, left, right. Let's just say the direction of bullet initially is positive. Okay. The wooden block was initially hanging at rest. It was stationary. So let's cross one of these terms off and make it 0. So I guess M1 is the mass of the bullet, 0.005 kg. velocity of 400 meters per second equals, we got to add the masses together. Notice that the mass of the bullet, or the mass of the combined system, is just barely more than the mass of the block itself because the bullet is so light. Oh, that's not equals, it's V. Okay. So one thing to notice here, the bullet's very, very light, the speed is very, very big. This actually turns out to be not that much momentum. 2 kilograms times meters over seconds equals 3.005 V. Did that wrong. Oh no, I didn't. I don't know why. I'm all sorts of messed up today. Okay, 0.67 meters per second is the velocity of the combined system. Now I want to point something out. If you didn't add on the mass of the bullet, if you didn't take into account the mass of the bullet here, you would get pretty much the same thing. Okay, very, very similar. However, I would not give you full credit for that. Okay, with conservation of momentum, sometimes that happens. Sometimes you have answers that are very, very similar, but you did something kind of fundamentally different. I am actively checking to make sure you're setting these problems up right. Okay, so you need to make sure you know how to set them up. And you need to make sure you're not just multiplying and dividing random numbers. You need to make sure that they're set up correctly and that you get the final answer that you should. Okay, just like with everything, but I just kind of an extra warning here because it is possible. Like if you had left this off, you would have got something very, very similar. However, based on what you have written down for your work, I either give you credit or I don't. Okay, or I give you partial credit. In any case, that bullet moving really, really fast embeds and can actually make that block start moving. But because the mass of the block is so much more and the momentum has to be conserved, because the mass is so much more, the velocity is going to be a lot less. Now we're to our explosion question, and I should have fixed this. This should say explosion, not collision. 2 lab carts that are initially connected together at rest explode away from each other. That just means that they were initially together and now they're moving apart from each other. It's not really an explosion, and I can show you this multiple times in class. One cart has a mass of 6 kilograms and has a velocity of 3.2 meters per second west after the explosion. If the mass of the second cart is 4.8 kilograms, what is its velocity after the explosion? Once again, we have to check to make sure that there's no net force. Okay, there is no net force in this case. It doesn't say anything about any sort of slope, so gravity is not accelerating these in any fashion. There's no friction to speak of, nothing else. We're going to assume that momentum is conserved. Pi equals Pf. Interestingly, there's one object before the collision, m1 plus m2 v, but 2 objects were initially connected together at rest. It means they were at rest to begin with. So this entire side is going to be 0. Pf, there are 2 objects afterwards, so m1 v1f plus m2 v2f. That's weird. 0 momentum, but we have objects that are moving afterwards. How could that be? Remember that momentum is a vector, and vectors mean direction matters. So if one object goes in one direction, the other object has to go in the opposite direction. When we add in the negatives and we add those 2 momenta together, we get 0. At least that's what we should get. So I have 0 equals the first cart, let's say a mass of 6 kilograms, and okay, velocity west, let's make that positive. Again, it really doesn't matter if you make east positive. You're going to get the same, you're going to get an answer that means the same thing. You just might have an extra negative sign or something, or the lack of a negative sign on your answer. 6 kg times 3.2 meters per second, it's going to be positive, so to the west, plus 4.8 kilograms, and we're looking for that velocity. Now what some people try and do, maybe I shouldn't even mention it, but what some people try and do is they'll think to themselves, okay, well if this is moving in the positive direction, this has got to be moving in the negative direction, so I'm going to put a negative sign on here. Don't do that, okay? Never just throw a negative sign on because you think something's going to be moving in the opposite direction. If you're not talking about a number, never put a negative sign on a variable unless it's stated in the equation to do so. Okay? Trust the math. We know that the final velocity of this cart should be to the east. So it should be negative. Let the math work out, because I promise it will. 6 times 3.2 is 19.2 plus 4.8 V2F. I'm going to subtract that over to the other side. Minus 4.8 V2F minus 4.8 V2F. I end up with negative 4.8 V2F equals 19.2. Divide both sides by 4.8, negative 4.8, excuse me. Let's move this up a little bit for you. And I get that V2F is equal to negative 4 meters per second. And I'm just going to put in parentheses, this means east. Okay? Watch what would have happened if we would have made this negative. That would have been negative. I would have had to add it to the other side. And then, when I divided, I would get a positive number, which would make it seem like it's to the west. Okay? Don't assume, don't put negatives on variables unless it's called for in the equation. If you think something is going to be in the negative direction, that's fine. Just trust that the math will work out like it did in this case. I ended up with a negative just like I expected. That's really it for conservation of momentum. I can't prepare you for every scenario that you could see, but I can prepare you for a bunch of different ones. Okay? It seems a little confusing at first with all that expanding of the equation, but really when it breaks down, you know, this is a very simple method for figuring out what happens before and after a collision. And that's really why momentum is useful, or conservation of momentum is useful. The details of any collision or explosion are messy. There's objects that are pushing on each other in all sorts of ways. Conservation of momentum shows us that if we know the initial conditions and the final conditions, or enough about the initial and final conditions, that we can determine whatever we need, whatever we're missing, whatever information we don't have. That's it for our momentum unit. Our next unit is going to, in physics, we kind of consider it going alongside momentum. It's called energy. It's actually a longer unit than this was. And energy is one of the most important units in physics, right up there with forces. Forces and energy are really the two big units as far as mechanics go that we really focus on. Not to say kinematics and momentum weren't big units, but they kind of play like supporting roles. Okay, forces and energy are really some of the two most fundamental topics, and they extend into lots of other things. So we'll talk about that next time. Until then, I'll see you later.